Very good morning, students. Am I audible?
Good morning, ma'am.
Happy to see you people again. As I was on leave in the last week. Very good morning to one and all. Hope I am audible. Yeah, good. Can you switch on your videos just for a moment? Good. So, all are at hometown, staying with parents.
Yes, ma'am, most of them.
Yes, okay. Okay, so what was done in the last class? So, I just need the feedback, what you understood, what they covered.
Pelton wheel.
Pelton wheel turbine, okay. So, rest are all not comfortable in switching on video. Okay, no issues. If you are not comfortable, don't do. Not an issue. Okay. Yeah. So actually, what I'll do is I'll just continue with where I stopped. So when the particular content, whatever is covered by the other teacher comes in, so we'll just have a discussion and then we will move forward. So let me have the flow continued so that you will have the better understanding. So that's what I'm planning. I hope many of you are attending today's session. So still only 28 out of 40. So what about others? Any particular reason? Yes? Anyone knows? Okay, so from next time onwards, please do join uh, in time so that let us not wait for all to join and all those things. Okay, so if there are any technical issues, that's okay. But better to be in time so that we can save time and we can use that time for discussion. Okay, so before I just start with the contents, I'll just try to recall what we have done in the last class. So we were discussing about the steam and its properties in the last class, where we have understood how to generate the constant pressure steam, okay, steam generation in a constant pressure process that we have went through. So for today's session, I'll just use the PPT where you will understand what we covered in the previous session. So I'll just run through the things and I will give the continuity for the next topic. And we will have one activity also today. Let them join in another 5 minutes so that everybody can participate in the activity. So have you understood Pelton wheel concept? I'm
Yes,
just trying to share the screen. Yeah.
ma'am.
Okay. So are the things clear to all of you? The Pelton wheel?
Yes, ma'am.
Okay, fine. Very nice. I hope the screen is visible.
Yes, ma'am.
Yes, ma'am.
Nice. Yeah, this is how you need to participate in the sessions. Don't be in a mute mode. Okay. So whenever it is required, please unmute and speak and discuss if you have not understood the things. Okay. Yes.
Yeah.
So the very first topic in Unit 3 was steam and its properties and the property chart. So we stopped at at properties. So we have not discussed the property charts, but of course we'll see in today's session. And then I'll give the lead to the steam turbines. So that is how we have to go. So once we understood how the steam is generated, so then we have to see where it is applicable or where it is used. Okay, then we will move on to the hydraulic turbines. Actually, what the sir has done is the hydraulic turbines, the Pelton will comes under this hydraulic turbines. This is what sir has covered. So let me just go in a continuous manner so that you can give connectivity and you can make your own mind map easily. Okay, so that you can remember the topics. So all these things we discussed in the physical class. What is vapor? What is steam? I hope all of you have understood in that session and how the steam generation takes place. These are the diagrams what we use to understand the constant pressure steam generation, where we have clearly distinguished between the wet steam, dry saturated steam, and superheated steam. And this is the graph which is going parallel with the process. And we have understood what is sensible heat, latent heat, amount of superheat, and all those things. So can anyone just tell me what is vapor as per our discussion? Quickly. Yes, please.
Ma'am, it is
Partially evaporated liquid containing particles of vapor.
Very nice, very nice. So nice of you. Okay. Yeah, so then we have understood how this water, which is at 0 degrees centigrade, is converted to a dry water at saturation temperature, that is the boiling condition, and the beginning of the uh, uh, formation of dry steam. And at point C, we had the dry saturated steam, and later on, we have the superheated steam, which is superheated to a predetermined temperature. So this amount of heat required in this region, we say it as sensible heat, and this is as latent heat. The combination of sensible and latent heat, the sum of the two is termed as the uh, enthalpy of dry saturated steam. So then we also understood what is the amount of superheat equation and all those things in the previous class. So all that, whatever we discussed in the physical class, all that is included here in the PPT. For time being, I had shared the PPT which I have not streamlined properly, but now I will share this PPT after the class. So in the Google Classroom, you can just access from there and you can refer to all these things. So we have seen that what is sensible heat, what is latent heat, all that definitions are listed here and the corresponding equations also here. So you can just go through it. Okay. So what is the parameter with which we can understand the wet steam and the dry steam concepts? Which parameter lets me know how much dry or how much wet?
Dryness factor.
Dryness
Minus
fraction.
fraction.
It is not factor, it is fraction. Okay. Yeah. Can anyone tell me what is dryness fraction?
Ratio of dry steam to the total
Sir,
mass of dry and wet steam.
Very good. Very good. So if I say the steam is 78% wet, so what does it mean?
22%.
The steam is 22% dry. Very good. Okay. Yeah. So all these things we discussed in these equations also we have discussed. So why we go for superheating? So once we got this dry saturated steam, we do the superheating of the steam. So why we need that superheating of the steam? So why? Because this superheated steam is used for executing many of the tasks like um, it is being used in various turbines and all like steam turbines for power generation and all such things. Okay. So why? Because its capacity to do the work will increase. When we superheat the steam, the energy contained in the steam will be more and the capacity of the steam will also increase. Okay. So this superheated steam will result in the increase in the thermal efficiency so that you can expect the more output from it. Okay. So always we do superheating in superheaters, which receives its heat from waste furnace gases, which would have otherwise passed uselessly through the chimney. So whatever the output of these superheaters will be there. So the furnace exhaust gases will be there. Those things can be reused so that we can uh, uh, efficiently use the exhaust gases, and we can superheat the steam, and we get the higher efficiency in that steam. So to increase the capacity of the steam to execute the task, we go for superheating the steam. Okay, so these corresponding volumes also. Yeah. These volumes I have already indicated in the diagram. I'll just go back to that slide. So you had seen all these volumes, okay? So in the wet condition, we refer it as VF. In the dry condition, we say it as VG. And in the superheated condition, we say it as V superheated, okay? So similar to the enthalpy, we also have equations written for this specific volume. So what is specific volume? Not with respect to this steam. In general, what is specific volume? Yes. Am I audible?
Yes, ma'am.
Yeah, okay. So then what is specific volume? Specific heat, specific volume. When we say it as specific heat or specific volume or specific density and all such things.
It's a property of water at a defined temperature and pressure. So, like the specific volume will be volume of 1 unit mass of steam in given temperature and pressure. Similarly, specific heat also.
Here, per unit mass is the driving force. Okay. So whenever I say specific volume, so it is per unit volume. Okay. Like that. Whenever I define a property per unit mass, then we say it as specific property. Okay. So here the specific heat or specific steam, specific volume. So all those things are referred with respect to the unit mass. Okay. So that VF is referring to the wet condition, and VG will be referring to the dry condition, and V superheated will be referring to the superheated condition. So those are the corresponding volumes of the steam at different stages. Okay. So here, if the steam is wet, then like two-phase mixture, then we say take the dryness fraction into account. So X into VG gives me the volume of the wet steam. Okay. So if it is completely dry, then it will be equal to Vg. Okay. So if there is a wetness in that, then X has to be taken into consideration. If it is superheated, then we go by the Charles law. So from Charles law, we have Vg by Ts is equal to V superheated by T superheated. So from this expression, we can derive it V superheated. So all these things are just for your understanding purpose, just for definition. So what are the different properties of the steam? No derivations are involved in it. So you can just go through these equations. Okay. So from this Charles law, we can arrive at V superheated. That is volume of the superheated steam. Okay. That will be equal to, you are taking this y value, that is V superheated, which is in the numerator, into consideration. So T superheated will go on the other side. Okay. So it will become V superheated is equal to Vg into T superheated divided by T saturated. Okay. So this is the property. So then I had explained you in the class also, so where that heat energy goes after the complete conversion of the water particles into vapor. So in the continued supply of heat, uh, where it will be utilized, where it will go. So that will be utilized in the form of displacement of the piston. So that displacement of piston, as you can just visualize with all these diagrams, the position of the piston is getting changed. Okay. That is called as the external work of evaporation. This I had told you in the class also. So the energy, whatever we are supplying, it is not only getting utilized for this conversion of water into steam, the excess amount of heat is getting utilized for displacement of the piston, which is termed as external work of evaporation. Okay. So what is the equation for work done? You might have studied in your 10th or 10th plus 2, 10 plus 2 level. Yes,
Pressure into volume.
pressure into volume. So same concept only we are using here also. So external work of evaporation per kg of dry saturated steam, that will be equal to pressure into the change in the volume, P into dV. That is what is the equation as you have studied. So W is equal to P into, sorry, dV. That is change in volume. Okay. So here what is the change in volume? So since I am addressing to the dry saturated steam, so I have to take Vg minus Vf. Okay. So Vf is very much negligible, as you all know. In the previous equations also, we have neglected 1 minus x into Vf. In volume equation also, we have neglected this term because it is very less. Considering this as very less, so we are neglecting this Vf term. Okay. So external work of evaporation for dry saturated steam, it will become P into Vg. Okay. If it is for wet steam, then dryness comes into picture. So P into X into Vg. Wherever this X comes, that means we are talking about the wet steam because we are considering the dryness fraction into account. So if it is superheated steam, then the work done will be equal to P into V superheated. Okay. So these are the expressions for external work of evaporation. Okay. Is that clear? Yes. Any doubt up to this?
Yes, ma'am.
So what we have discussed so far, if we have taken the expressions for enthalpy, expressions for specific volume, expressions for external work of evaporation. Okay. So everything remains the same. Okay. For enthalpy also, if it is wet steam, we have taken X into consideration. If it is dry steam, no need to take X because X will be equal to 1. Then if it is superheated steam, we have taken the superheated condition, and that is amount of superheat into account. Okay. So similarly for specific volume and the external work of evaporation. So this is all about the steam and its properties. I just try to go back to your enthalpy equations. See. So if it is dry enthalpy of dry saturated steam, it will be HF plus HFG. So if it is wet steam, then HF plus X into HFG. So here we have the X term since it is wet steam. Next is superheated means H superheated is HF plus HFG plus this amount of superheat. Okay. So here I had explained you the other day one more concept. Why we are considering CPS and when we consider CPW, that I had explained you in the physical class. Okay. Yes. Yes, Somisha.
Ma'am, will you be sharing this PPT on the classroom?
Definitely, definitely. I'm going to replace that PPT with this.
Okay, ma'am.
Yes, for time being, I had shared you because I was on leave in the last week. So I thought let's not have a discontinuity so that if I post that, you people can have the continuity and you can go through that PPT for time being. So
Okay,
thinking that I had shared that. So this one I will share. This is the updated one which I use for class. Okay, so I'll share this. I'll replace that old file with this.
Yes, ma'am. Thank you, ma'am.
Okay. So if it is in a steam condition, so if it is after the dry saturated steam, so we take CPS into account, specific heat of steam. Okay, that we take into account. So if it is in watery condition, means if the process is not starting from zero, then we use CPW. So these values, it will be 2.25 for CPS and 4.18 for CPW. Okay. Yeah. So this I think I had shown in the class with the graph here. So this is what is the amount of superheat. Since it is after dry saturated steam, we take CPS into account here. Okay. If the process is not starting from zero, if it is starting from some temperature here, then our sensible heat is not from the origin, it will be from here to here. Okay. So in such condition, we use CPW because it is in the water region. Up to A to B, it is still in water, liquid condition, not in steam. Okay. Yeah. So is that clear up to this? Yes.
Yes, ma'am.
Okay. All of you. Any doubt?
CPS is heat capacity of steam and W is heat capacity of water.
Yeah, definitely. Yes. Any other doubts? Shall I proceed? Shall I proceed?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So I want everybody to interact. As I told you, don't keep in mute mode and just uh, keep quiet. Okay, so you just respond to me so that I'll get confirmed that you people are actively participating. So earlier we used to have some numericals on these properties of steam. So at that time we were using these tables, steam tables, which are called as steam tables. There are two different types of steam tables. One is pressure based, another one is temperature based. Here in this pressure based, for a given pressure, we used to get the saturation temperature and sensible heat, latent heat, enthalpy of dry saturated steam. All these values we used to get, and using these tables we used to solve the numericals. But for your syllabus, there are no numericals. Just for awareness, how the steam table will be. This is included in the presentation. Okay. So this is pressure based, where the pressure will be given. This column will be given. For a given pressure, what are the other values we have to take from the table, and we have to substitute in the equations and find the other values, required values. Okay. The other one is this temperature basis, where we will be given with the saturation temperature, and this column will be used to obtain all these values, and the corresponding values can be utilized for finding the other properties. Okay, so these are the two different tables. So can we have an activity now? All of you are ready?
Yes, ma'am.
Yeah, fine, very nice.
Yes.
Okay, so let me just click on this. Be ready with your paper and pen. So I have a puzzle here, so which is related to steam and its properties, whatever the topics I have covered so far. So I want all of you to find the terminologies with respect to the steam, the different types of steams and all. So I want all of you to identify the words related to the steam and its properties. So is the screen visible? The word file is visible to all of you? Yes or no?
Only one screen.
Ma'am, it says activity, that's all.
Ma'am, it only says activity, that's all.
Okay, so it may be taking time. We'll just wait for 3-4 seconds because here it has opened for me. Now,
Yes, ma'am. Now we
Yes,
can
ma'am.
start.
yeah, here the activity goes. So I want all of you to identify the terms which are related to steam and its properties. It can be type of steam, it can be property of the steam, whatever it may be. Okay. So just find the words in the puzzle.
Should we write it down on the paper?
Yeah, should we? You have to write it on your paper. If you are done, you can raise your hand. I'll ask one by one. So I'll give 3 minutes to all of you. Not three, just 2 to 3 minutes. Okay, you can take 2 to 3 minutes. If you are done, you just let me know. I'm done, so that I will end the time. I can ask.
Ma'am, how many are there?
Sorry,
Words are
your voice is breaking. So no need to write down. Just you write down the answers. Don't write down the puzzle here. Okay, so just write down the answers. If you want me to tell the number of words, I think here there are 5 words or 5 properties. Don't type the answers in the chat box. Everyone can see. If you are done, you just raise your hand.
Only 5 words, no, ma'am?
Yeah, 5 words. Done? Anybody?
Yes, ma'am, done.
Mola.
Yes,
One.
ma'am, done.
Okay. But no one raised your hands. Anirudh, done?
Ma'am, I got 3. Not done.
Okay, so can I have your name? Who has done?
Nidhi, ma'am.
Nidhi. Yeah, okay. Now I can see your hands. Yeah. Okay, Nidhi, can you just go ahead?
Ma'am, I got dryness fraction,
Okay.
dry steam, sensible heat, latent heat, and wet steam.
Okay. Mihir? Mihira Gayatri?
Yes, ma'am. These itself, I found latent heat, sensible heat, dry steam.
Okay. Vijay? Okay, so let me just wind up with the answers. Yes, this is the answer. So we had 5 words here. Wet steam, dry steam, okay. Then sensible heat, dryness fraction, latent heat. So hope many of you got this answer.
Yes, ma'am.
So there are 5 words. Yeah. Shall we wind up?
Yes, ma'am.
Yeah.
Yes,
Now,
ma'am.
okay, fine. Now let me go back to the PPT. Okay. So now we understood so far how to generate the constant pressure steam, generate the steam in a constant pressure process. So that we have understood, and what are the properties of that steam also we have understood. So now let us see where it is being used. So what are the applications of this steam? Okay, before getting into that, we need to understand few concepts before actually talking about the steam turbines, where we use the superheated steam as an input to execute various tasks or power generation or things like that. So we have to understand what are prime movers and what is nozzle effect is being and how these steam turbines are classified. Then we will move on to the hydraulic turbines. I hope this is not covered in the previous class by other teacher.
No, ma'am.
No,
Okay, fine. Okay, fine. So what is a prime mover? Let's have a small discussion here. What's a prime mover?
What's the natural energy of the substance into mechanical energy?
So which converts the natural energy into mechanical energy. So any other answers?
In terms of water, the hydraulic water pressure is converted into electricity using its kinetic energy.
Okay, very nice. Anyone else? Anyone wants to give the answer here? What is a prime mover? In general English meaning. Okay, so what is a prime mover? So whom you can say as prime mover?
The main worker sort of thing.
The main worker, the main manager. Okay. Has any other answers?
It's like a source of, like it
Very-
helps in generating power.
Okay, very nice. So this is the source or driving force. Okay. Next, any other answers?
The main driving force behind anything.
Yeah, main driving force behind anything. Okay, very good. So a prime mover is one which is the key element in that entire process or the component. Okay, so which is acting as a driving force, isn't it? So a prime mover, if you just talk in terms of energy conversion and all, so it is a device which takes any type of energy as an input and converts that into some useful task. Okay, so it can be a mechanical movement or anything. uh, any source of energy is taken as input and the output will be some work. Okay, so such a device which takes the energy at input and converts that into some useful work, such devices are called as prime movers. Okay, if it is using some heat energy at input and giving out some mechanical energy as an output, we say it as thermal prime mover. If it is using the water energy, okay, so as an input and converts that into some mechanical task, then we say it as hydraulic prime mover. Okay, so very similar. Can you just quote some examples over here for prime movers? So I said it can be any form of energy at input, but some useful work at the output. So that conversion is done by a prime mover. Okay. So if it is using heat energy at the input and executing some mechanical task, then it is called as thermal prime mover. If it is using water energy and executing some mechanical task, it is called as hydraulic prime mover. Okay, so the examples are given here. So they are in the PPT itself. Okay. So what are thermal prime movers? Which are thermal prime movers? Can anyone just give me some examples either for thermal or for hydraulic?
Steam turbines. No?
Okay, very nice. Next, anybody?
Heat.
Combustion engine.
Very good. IC engines. Very nice. Next.
Stirling engine.
Sorry, pa?
Stirling engine.
Turning engine. Okay. Next.
Steam engine.
Steam engine. Okay. Very nice.
Oh, water wheel.
Very good. Water wheel.
Won't water be hydraulic?
Yes, ma'am. Water wheel would be hydraulic, right?
Yeah. It is an example for hydraulic. Okay. No problem. Next. That's what you have studied in Peltan, right?
Yes, ma'am.
Yeah. Good. Next. In hill stations, have you seen those big fans running?
Windmills, ma'am. Windmills.
And windmill.
Very good. That is also an example for a prime mover, which takes the wind energy as an input and helps in power generation. Okay. So it can take any type of energy at the inlet, but ultimately it should convert that energy into some useful work. So that is nothing but a prime mover. Okay. So here in this particular chapter, we are discussing about the steam turbines, hydraulic turbines, and gas turbines. So these are the three different turbines what we are covering in this particular unit. Okay. So before we get into this steam or hydraulic turbines, we need to know the concept of this nozzle effect. So this is very important concept. Okay, you should understand this very well so that it will be easy for all the three types of turbines. Okay, if not three, at least for two types of turbines, steam as well as hydraulic turbines. So let us understand what is this nozzle effect is. So we have, you all know what is nozzle. Okay, so it will be having a diverging and converging the area, that region it will be having. So the water or the fluid, whatever it is there, it will be sent through that nozzle. So as it is having the variable area, so a variation in the cross section, there will be obviously a few parameters getting affected by that. Okay, either it can be velocity or pressure. Okay, so how these nozzles are designed? What happens to the energy at the inlet and energy at the outlet? What happens to the property at the inlet and property at the outlet? How they are varied? So that is what is very important, and we are going to understand that with this concept of nozzle effect. Okay. So as you can see in this diagram, I hope my cursor is visible to you.
Yes, ma'am.
Okay. So as you can see in this diagram, so we have this entry. We have taken this right side as exit. Okay. So here we have from entry to this throat region, this narrow region, we say it as throat. From entry to throat, we say it as converging area region, converging region. Okay. Means the end is pointing towards some narrow area or narrow cross section, okay, or reduced cross section. Okay, so here I have large area at the inlet and which is getting diminished as it reaches towards the throat. Okay, then from throat till this exit, we say it as divergent area, means it is opening up. Okay, it is enlarging, it is increasing, the cross sectional area is increasing. Okay, so this is the structure of this nozzle. So when we pass the steam or water at the inlet, it will be having very high pressure and low velocity. As I told, it can be steam or water. If it is a steam turbine, we take steam. If it is water turbine, we take water. So at the inlet, it will be having high pressure and low velocity. So when it passes through the nozzle and crosses the throat region and exit from the throat region, and when it reaches the exit, so it will be having low pressure and high velocity. So at the entry, high pressure, low velocity, and at the exit, it will be having low pressure and high velocity. Okay, this pressure energy is converted into the velocity. So it will be gaining very high velocity. Okay, so how it is happening, how this effect is happening. So let us try to understand this with an analogy. Okay, so you people are sitting in one classroom. Okay, am I audible?
Yes, ma'am.
Yes, ma'am.
Okay, so we'll just try to understand this concept, the nozzle effect. So all of you are sitting in a classroom, the closed classroom. So when you people are sitting at your own places, so things are fine. Okay, so there is no too much of crowd or rush. It will not be there. So number of chairs and number of people, so it is equal, and you people are comfortably sitting in at your places. Okay. So now the class is over. What happens? So all of you start moving from your desk and you will start going towards the door. Okay. So classroom is free, occupied spaciously. But when you start moving to the door is nothing but the throat region. Okay. When all of you rush towards the door, so crowd will increase at the door region. So what happens to the pressure? What happens to the pressure? When the
High pressure.
Increases.
pressure will be more because crowd is more. So
The pressure increases.
increases exactly. So when all of you rush towards the door, So the door is very congested area. So you cannot, all of you cannot run through the door or pass through the door at one shot, isn't it? So there will be crowd. So the pressure increases. So velocity will be low. It will be low because you cannot run in that region because the crowd is more. Okay. So near the door, the pressure will be more, velocity will be less. So as soon as you cross the door, as soon as you step out of the classroom, so you can move in any direction. You are free to go in any direction. Okay. So all of you can walk in different directions and the so that the pressure decreases and velocity increases. You can run also. Nobody stops after crossing the door, not even the teacher, isn't it? So velocity will be more, pressure will be less. So that is what happens in the nozzle. Am I clear? Yes, please.
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
People are following what I'm explaining?
Yes, ma'am.
Yes, ma'am.
Okay, fine. Okay. So this is what is nozzle effect. So at entry, it will be high pressure and low velocity. And at exit, it will be low pressure and high velocity. So this concept is utilized in the turbines to control the flow of water and its parameters like pressure and velocity so that you can control the motion of the rotor, which will be in turn connected to a uh, generator and we can go for power generation. Okay. So in this, this is the turbine which is going to be used in these steam or hydraulic turbines. Okay. So you can see in this picture, these are the different components which are there in the turbine. So we have a rotor at the uh, outer side. Okay. So this is the central shaft on which this rotor will be mounted. Okay. So on this rotor, we will be having the blades. These number of blades is also another component which needs to be taken care while designing the turbine. Okay. So I have shaft at the center. On this shaft, we have rotor mounted. So on the outer periphery of this rotor, we have blades. Okay. And this is the nozzle through which the water or the steam is flowing. So that water or steam which is coming out of this nozzle will strike these blades so that the rotor sets into motion. Okay. So we have blades, nozzle, rotor. Casing is the one which covers the entire component. Okay. It is not shown here actually. Okay. So casing is the one which covers the uh, this entire thing it will be housed inside the casing. So this you have seen in the Pelton, right? So it can be this fashion if it is Pelton turbine. So it can be the spiral thing if it is a Francis or Kaplan turbine. Okay, this is nothing but casing is nothing but the outer cover. So these are the various components in the turbine or parts of a turbine. So based on how this pressure and velocity is varying, based on this, we have two different types of turbines. One is impulse, another one is reaction. Okay, based on the cross section of these blades, the variation in pressure will be different. I hope you people are getting what I'm drawing here. Okay, so here I have uniform cross-sectional area in this blade. I have uniform cross-sectional area, whereas here this is not uniform. Okay, so here the area is different, cross-sectional area is different here, and it is different here. So this is varying cross-sectional area. This we call it as aerofoil design. Okay, this aerofoil structure, whereas this is it is uniform. Okay, this is uniform cross-section. So how these blades are designed and how the pressure and velocity are changing as it glides over the blade. Depending upon that, we have impulse turbines and reaction turbines. Okay. So we'll just try to understand these two types of steam turbines. So in impulse turbine, the water potential energy is converted into kinetic energy by nozzle, and jet of water is directed on the turbine's curved blades, which will reverse the flow. Okay, so we'll just see how it is happening. Yeah. So this entire setup is for impulse turbine, and this is for reaction turbine. So here we have this uniform cross section of these blades, and whereas here we have the aerofoil structure. Okay. So in reaction turbine, we will be having fixed blades and moving blades arranged in an alternate fashion. Okay. These are called fixed blades, and these cream colored one are moving blades. As you can observe here, there is no nozzle provided here. But here we have nozzle. This is nothing but the nozzle. And we have these blades, moving blades. Okay. So since they are of uniform cross section, okay, pressure is not going to alter as the water or the steam glides over this blade. Whatever the changes that are there, that is the pressure changes, that will be happening in the nozzle. Okay. So as it glides over these moving blades, because of their uniform cross section, so there is no change in pressure. The pressure remains constant. You can observe in this graph, the orange line represents the pressure, the green line represents the velocity. So as the steam passes through the nozzle, its velocity increases and pressure decreases. That is what you have studied in the nozzle effect. Okay. So velocity increases, pressure decreases. Okay. So as the steam passes through the nozzle, so you can see there is a drop in the pressure, but increase in the velocity. Okay. So all of you are following what I am explaining?
Yes, ma'am.
Very nice. Anyone wants me to stop at this point, or anyone wants me to go back? Yes? Okay, so shall I proceed? Sorry? Definitely. So your Pelton wheel, whatever you have studied, the other teacher has taken, no? So that is an example for impulse turbine. Okay. Francis and Kaplan, what you are going to study in today's class or in the next session, those are the examples for reaction turbines. So I will be taking you through these three types of turbines, which are the examples for both the kinds. Now you just understand what is happening in impulse turbine and what is happening in reaction turbine. So that comparison I am trying to make you people to understand. So just concentrate on this. Okay. So I will give you the detailed classification with examples for both the types. Shall I proceed? Oh, fine. So here in impulse turbine, there will not be the fixed and moving blade concept, because if here whatever the pressure and velocity changes are there that are achieved through this nozzle. So here we will be using the nozzle. So wherein as soon as the steam passes through the nozzle, its pressure decreases and velocity increases. So this region is representing the nozzle region. Okay. So next one is the moving blades, which are having uniform cross section. So here, as the water glides over this blade, because of their uniform cross section, there is no change in pressure. Pressure remains constant. You can see here the pressure line is straight line. So the pressure remains constant, whereas the velocity decreases. Okay. So this is in impulse turbine. If you just look into the reaction turbine, the nozzle effect is provided by the aerofoil structure of these blades, the fixed and moving blades. Okay, just a second. So is the PowerPoint visible? Okay. Yeah. So the nozzle effect is achieved through these alternate fixed and moving blades and out of their aerofoil structure. Okay. So as you can see here, this itself provides the nozzle effect. The blades itself provides the nozzle effects. Okay. So here what happens, as you can see, as soon as the steam glides over these blades, there is drop in pressure in both the regions. Okay, because of the aerofoil structure. Okay. So in the first set, that is in the fixed blades, there is increase in velocity. In the moving blades, that energy is utilized for setting the rotor into motion. Okay, so the blades are getting moved. Okay, then the velocity is decreasing in the moving blades stage. Okay, so first stage in the fixed blade region, velocity is increasing. In the moving blades region, it is decreasing. So this is the difference between impulse and reaction turbines. Okay. So in case of these impulse turbines, they are also called as D-level turbines, and reaction turbines are also called as Parsons turbines. Okay, so these are the two types of or the two concepts which we use in the turbines. Okay, so now as I told, we take the Pelton wheel as an example for impulse turbines, and Francis and Kaplan turbines are considered as examples for reaction turbines. We'll just see how they are. If you want me to just summarize the difference between impulse and reaction turbines, need not be water, so it is applicable for both. So there is no pressure change of the fluid in the turbine in case of impulse, because we use what we use. Yes. It is saying no pressure change of the fluid in the turbine rotor blades. So there is no pressure change in the blades. Where it is changing? What we use in nozzle. Very
Inside the nozzle.
Very good, very good. We use nozzle in case of impulse turbine. The change in pressure is achieved in the nozzle. Okay, so here in case of reaction turbines, the pressure of the steam or the water changes as it passes through the turbine rotor blades. Okay, so in impulse turbine, they do not require pressure casement. Okay, they won't require any containment of the pressure and such. But whereas in case of this reaction turbine, it requires a pressure casement. Draft tube is not necessary in impulse turbine. Draft tube is necessary in reaction turbine. I'll come to this draft tube. This concept I will explain when I get into the these turbines. Okay, I will explain it there. When impulse turbine, the Newton's second law describes the transfer of energy, whereas here the Newton's third law describes the transfer of energy. Okay, so this is an assignment for all of you to look into what is Newton's second law and Newton's third law. This I'll take up in the next class, and I'll ask you people. So you have to explain me what is Newton's second law and Newton's third law. Okay, before I start this explanation, I want all of you to discuss that. Okay. Okay. So here are the hydraulic turbines. With respect to steam turbines, if you just know what is impulse and reaction, that is sufficient. So if I come to these hydraulic turbines, So we have these three types in which Sir has already started with the Pelton. So I will take up the other two in the next class. Is the time up?
Yes, ma'am.
Okay, okay. Then I'll stop at this point. Francis and Kaplan I'll start in the next class along with classification. This classification has been discussed by the other teacher.
Yes, ma'am.
Okay. Okay, then I'll just run through quickly through this and then we will look into the Francis and Kaplan in the next class. Okay, this I will just concentrate in the next class. So any doubt in this session? No. So all of you understood what I have explained?
Yes, ma'am.
Yes.
Yes, ma'am.
Okay. Thank you, students, for joining. Have a nice day. We'll
Thank
meet
you,
in the
ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you,
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.